So today we are going to start with a consideration of individual trajectories via stochastic differential equations. But unlike the beginning of the course where we proceeded purely naively, now we are of course armed with our understanding of stochastic processes, right? In particular continuous Markovian stochastic processes. And what we will see is that the kind of trajectory we are interested in is an example of such a process. So we can use what we have understood so far to systematically develop the mathematics of SDEs. So a good starting point is to think of a one-dimensional process, right, which satisfies something like an SDE, and then we'll be able to formally define what we mean. So we want to consider trajectories, okay. So x is a function of time, right? Let's think of it only one dimension. Let's say you have x, or think of it as a particle moving around, like a Brownian particle, and it's some fluctuating quantity of time, okay? And therefore it's a stochastic process. Now what kind of process it is, we will be more precise in a second, but certainly x is some function of time, and it's not some smooth deterministic function, it's some stochastic function, okay? So it can be a stochastic process, just like the stock market price or and so on, right? And we want to think of x of t such that it satisfies our SDE, right? In other words, x of t is such that I can write something like this. Now we will of course refine this, but I want to start with the naive idea of a stochastic equation, okay? And then we will refine it. But what I have in mind is some x of t which satisfies something like this. Okay, so this is the kind of general way of writing it, right? So it looks like an ODE, right? If I just had this, it would be our usual ordinary differential equation. But what we have now is not only the deterministic kind of velocity, if you like, but we also have a stochastic part, right? So we have a coefficient b, which is also some function of x and t. So it's something like, it could be sine x cos t, right? This is just a function. But it's multiplied by this stochastic forcing, okay? And that's why it becomes different from a usual ODE. And now what are the properties of this? This thing is what contains the stochasticity, right, that we are interested in. So we are going to look at cases where the mean, right, the angular brackets denote the mean over the ensemble, which means, let's say zeta of t is some, has yet to be defined, but fluctuating function of time, right? And I can generate many such trajectories of this zeta, right? Because it's random, I generate one, somehow tossing coins in some way, and I can generate another, and if I average over them, right, I'm saying the mean will be 0. So 0 mean, and then I want to say something about its temporal correlation, which is what makes it fluctuating. So if I look at this covariance, if you like, at two different times, t and t prime, I want it to be uncorrelated in time, okay, because this is what the random steps look like, right? So if you think back to the random walk, and I think of this as the random force, right, that is acting on x to make it move. The whole idea is that the kind of random forcing at some time is completely uncorrelated with the forcing at the next time instant, okay? Right, and that is represented by this in the delta function. So if t is not equal to t prime, no matter how close it may be, it's completely uncorrelated. It's, of course, you will recognize this as something that gives you a measure of correlation, right, over a statistical signal. Right? So if the correlation is 0, it's uncorrelated. And so you see that it's completely uncorrelated at any time difference, right? Only if the time is the same is there a correlation. And now there you will see that that correlation, of course, would be the variance, right, at the same time. And so you see that the variance when t is t prime is infinity, right? So you can stop me and say, why are we taking it like this, right? We understand why we want there to be no correlation in time, but why should the variance be infinite, right? That's a fair question now. We will come back and see why we have to take it in this way, right? But you could have also said, okay, I'll define a function which is 0 for any non-zero argument. When t is not equal to t prime, it's 0. If t is equal to t prime, it's some value, bounded value. This won't work for our purposes, we will see in a second. So, but it's a fair question at this point, right? So let's keep a pin there and we'll come back. But for now, let's say, okay, there's a delta function. Now at this point, so this is what gives it a fluctuating, I mean, that's what we mean by fluctuation. But of course, there can be different fluctuating signals which don't have delta correlation, right? So you could have something that is still fluctuating, but which is correlated. In fact, X will be such a process. Right? So I'm looking here at the correlation of zeta, but these fluctuations will of course create fluctuations in X, right? That's the whole idea. And I can look at this same quantity for X. Now X will have some correlation, right? Because of this part. Right? This is a deterministic part, right? So it will give you some correlation in X. For example, if this is just equal to minus X, suppose this function was minus X, then there would be an exponential decorrelation, just as an example, right? So this part will certainly give you correlations. Of course, this part is also there. So X would be an example of something that is fluctuating but is correlated in time. That means that if I look at this quantity, it will be some function of the difference t minus t prime, right? If it's a stationary process. So why am I taking it to have no correlation? Okay, the reason really is because we want to make some general mathematical progress, right? I want to understand the behavior of this SDE, right, in a way that has some generality. Otherwise, if I put some correlation here, some functional correlation, then anything about this equation depends on what I choose, right? I can make it exponential, I can make it decay in some way, right? And then there's no hope for having some kind of general theory, right? Any answers you get would have to be more or less numerical and would depend on this choice. And of course, there's no particular reason to choose anything. Yeah, because the whole idea of using SDEs to describe physical processes is that there is some very rapid phenomena going on. For example, these molecular motions, right, in the fluid that are creating the net, that are bombarding my Brownian particle, creating the net force, right? So it's those molecular fluctuations that are at much rapid time scales which I don't care about, that I'm trying to get rid of and model via the random forcing. Okay, so the whole idea is I don't want to worry about that. Now, if I start putting some kind of correlation here, the first question will be what correlation, right? And there's no way for me to answer this unless I go deep into the small scale processes, which is the whole point is I want to forget about them. Okay, so the obvious thing to do, which allows me to not worry about all those details, is to take the delta correlated limit. So I say that, okay, there is some correlation, of course, because it's a physical process, right? Nothing is changing instantaneously. There is at some small, if you zoom in, there will be some mechanistic thing that is happening, so that the future will be correlated to the past, of course. But that is happening at such small time scales that I don't care about it. I'll just say it is completely decorrelating at the time scale of interest of the quantity x, right, which may be the motion of my Brownian particle. So I'm basically saying I'm interested at the process x over such times that whatever correlation is extremely small. Now this idea is important because later on we will appeal to it when we model physical processes, right? To say that the SDE I'm interested in is really the limit of vanishing correlation time of some fluctuating forcing, right? So we'll come back to that. But for now, as a mathematical treatment, we say, okay, that it is zero correlation. Okay, so that's the motivation for making it delta correlated. Okay, so I don't have to worry about the processes leading to this. Now, why it should have infinite variance, as I said, we'll come back to. Okay, so let's leave it there for now. Okay, so this is our starting point. It's basically the Langevin equation, which is kind of a naive way of thinking about a stochastically forced dynamical system. And of course, there are problems with this mathematically, because what we are saying is dx dt, to write it, we are assuming that x is differentiable, which means the derivative is bounded. But of course, we have a term here which is unbounded, right? The variance is unbounded, which means I can have arbitrarily large derivative values. I cannot say that the derivative is well defined, yet I am writing it down. So that is exactly the problem. Even beyond that, if I want to do a numerical simulation of this, how do I do it? Right? Do you have some function which has infinite variance which you can sample to generate the noise? Right? It's not defined because of the variance being infinite. So how do I do a simulation? So there are all these problems with writing this naive kind of stochastic ODE. And that's exactly what we want to resolve in this class. Okay, so the way to make progress now is to use this as a kind of motivation, right? That I want to study X, which satisfies some kind of stochastically forced ODE. But to make progress, I should not think of this differential equation. Instead, I should look at the integral. Okay, so now that we have this picture, what we actually want to focus on, right? On the trajectory X. Okay, and the trajectory X comes from this, if I assume for the moment that it has some meaning, by integrating. Okay, so I will rather look at the trajectory X of t, right? And I can formally integrate that, right? So it's X at the initial time plus the integral right? So S is my integration variable, and I'll go from 0 to capital T. The same thing, right? Okay, any questions? So for the moment, I've written something down by way of motivation, right? And said, okay, let's look at the integral of that, formally speaking. So I can always write that integral and say, this is what I'm really interested in now. Okay, because what I want to do is to calculate somehow this trajectory to understand the properties of X of t, not necessarily of its derivative. Right? And I can see already that directly working with the derivative is problematic. So let me think of the trajectory. Then I can at least formally write it like this. Now the first integral, there is no problem. It's the usual Riemann integral, right? And its properties is what allows us to understand when an ODE, for example, if I forget about this, right? When is this ODE going to have smooth, unique solutions? That depends on the behavior of this, right? So that's well understood. That's the usual Riemann integral. And if this A is Lipschitz continuous, we'll have unique solutions to the ODE. So this is fine. The problem is, right, what is this? Okay, and does this make sense? Where this zeta is a randomly fluctuating quantity, uncorrelated in S with this infinite variance behavior. Okay, so what we will do to make progress is consider the simplest version of this kind of integral. Right? So the whole point of the next few classes is to make sense of this integral. If I can make sense of this, then I can make sense of X, and then in that same way give some meaning to the SDE. So to make progress, let us consider the simplest version of this where B is just 1. Okay, in that case, I just have integral zeta of S ds, and that itself is some stochastic trajectory. I'll call it U. Okay. Fine. Now, regardless of the status of the kind of pseudo ODE in 1, I can certainly consider this. Right? It's U of t is some stochastic process defined in this manner, where zeta has these properties, right? These statistical properties. That's certainly fair to consider. So what can we say about U now, just based on this definition? So of course, U is going to be stochastic. Is it continuous? So, and is it Markovian? Right? So definitely it's a Markov process, because by definition of the integral, right? So U at time t plus delta t only depends on U at time t, right? Because the value at t plus delta t is this integral from t to t plus. It doesn't depend on what came before. If I know U at t, I can calculate what's going to happen in the future because of the definition of its own definition, right? Similarly, because it's defined as an integral, it is continuous. So I know now that U of t is a Markov process, right, and is continuous. Okay. So what does that mean? That immediately means that the distribution of this U, right, and its properties, etc., everything can be understood through the Fokker-Planck equation, right, or that there is a Fokker-Planck equation for the evolution of this U, okay, for the probability distribution of all the trajectories of U. That's exactly what we have been doing in the past few lectures. So if the distribution of U and its properties are governed by a Fokker-Planck equation, what do I need to know to write down that Fokker-Planck equation for U? What are the two unknown things you need to specify for the Fokker-Planck? Anyone? Right, so if you look back to the Fokker-Planck equation, which we derive, right, for any general continuous stochastic process, what are the unknowns in that equation? Right, the A and the B, right, the drift and the diffusion coefficient. And how did we define them right at the beginning of the derivation? The drift is nothing but the first moment of the step, correct? And the diffusion coefficient is the second moment, right, divided by delta t, taking the limit of small delta t. So that's exactly what I can do directly here. So if I can find out the values of A and B, which are the mean moment of the increment of this U, correct, divided by delta t, and the mean of the second moment of the increment of U divided by delta t. So if I have those two things, I can actually write down the Fokker-Planck equation for whatever this U is directly. And from there, I can figure out how U is going to behave. Right, so let's do that. Right, so the A for the, right, so the PDF, right, of this U process, right, is governed by a Fokker-Planck equation, right, in which I will have certain drift and diffusion. Right? So remember, the drift is limit delta t going to 0, 1 by delta t of the ensemble average, right, of by delta U. So there, when we defined it, we used the PDF itself. We said integral of the U at t plus delta t minus U at t times the PDF of the transition step. That must be A. Right? So here I'm using the same thing. The angular brackets represents the ensemble average. And now I can get this delta U directly from its definition. Okay, so how will I write delta U? That is just U at t plus delta t minus U at t, right? Okay, so what is this now? I have the average. Can I write this difference in terms of the integral? Right, I just have to adjust the limits. No? So what should the limits go to? What should be the lower limit? Right, t to t plus delta t, no, obviously. Right, of this. Make sense? Right, and now I can pull the integral inside, the ensemble average inside, right? Because the integral over time, the ensemble and averaging operation are interchangeable. So if I bring that inside, and what is the ensemble average of zeta? 0 by definition. Okay, so this tells us immediately that A therefore is 0. So I have a Fokker-Planck equation with no drift. Okay, which makes sense, right? Because the zeta has 0 mean. So in other words, what you're saying is that if I integrate these zeta forcings over time, right, these taps, uncorrelated taps of infinite variance, right, if I generate a sequence of such taps somehow, I don't know how to do it, right, because this zeta has infinite variance, but suppose I could do it in some way, integrate over it, I would not have any drift. Okay. It would, the probability of where I would end up, right, that PDF would be governed by a diffusion equation with no drift. So I will have zero mean. That's of course by definition, not surprising. But now let's look at what its diffusion kind of behavior would be. Right? So if I construct many such trajectories by integrating over these, right, taps, right, I would drift off in different directions. The mean of where I end up after some time will be zero. I'll all be centered around zero. But there will be some spread of these trajectories, right, constructed by integrating over the taps, the infinite force taps. Right? So what would be that spread? That's exactly coming from the second moment, right, from B. So now I want you to repeat this exercise, but with the second moment. That just means you take delta U into delta U, which means I do this integral 2 times. So here I have integral over SDEs. You do the same integral, but introduce another variable, MDM, let's say. And then you take the ensemble average inside. So what will I get? Right, so 2 integrals, ensemble average I bring inside. Same operations that I did for the mean. Right, and now you see the utility of my definition of the covariance. Okay, so what I have appearing there in the equation for B is exactly this quantity with S and N with M, and we now use the fact that it's delta correlated, right, which will simplify that integral, and this is where the delta function will come in. Right? So we will see that now going back here. So if S is not equal to M, 0. Right? That's the meaning of having no correlation in time. Right? And if S is equal to M, for the integral to give me some meaningful value, I need to have that delta function. Right? Otherwise, even if this has some finite value when S is equal to M, the integral will vanish, right? Because it has a value only at a point of measure 0. So I need it to be a delta function for that integral over, let's say, ds to give me anything. So now you can see why for that tapping to give you some meaningful drift, meaningful spread, it has to be a delta function, right? The correlation of zeta. So when I do this, now I'll evaluate, let's say, S, it will just give me this M equal to S, right, with 1. I'll retain S. So I did the integral over M. And now, of course, sorry, that's it. Okay, replacing this with the Dirac delta function of S minus M will give me this. Now when I integrate, I'll just get delta T, right, divided by delta T, to become 1. So I'll get B equal to 1. Okay, so what we've found out, right, by starting with this integral, by just taking the integral of zeta, we see that it is a stochastic, continuous Markov stochastic process, right? Therefore, it's describable by a Fokker-Planck equation. And from using the integral definition itself to define the increments, I see that the mean of the increment by delta t is 0. The variance of the increment by delta t is 1, right? Which means it is just the Brownian, pure Brownian diffusion process, which is what I was after, right, from the beginning, from the first lecture. So to be precise, in terms of what we defined in the last class, right, this U is the Wiener process, right? Which corresponds to Brownian motion. Okay, so if for the moment now we forget about all the motivation that brought us to consider this integral, which was to start with this pseudo ODE, etc. If I just start from this and I say, okay, zeta is this delta correlated infinite variance kind of forcing function. If I integrate over it, I get something meaningful, which is in fact just my Brownian motion or the Wiener process. So the trajectories of u will be Brownian trajectories. And if I take the derivative of u, it's not differentiable, right? We already know this. Remember in the last class we looked at the Wiener process and we found out that its increments are independent, right? And it is continuous, right? Because it's a result of a Fokker-Planck equation. But it is non-differentiable. We proved this in the last class. And here we can see it directly from this different root, right? Because if I take the derivative of u, it is zeta. Zeta is not, of course, meaningful. It's infinite variance. That also makes sense why we had infinite variance, because du by dt or this thing is not bounded. It's not differentiable. But I can certainly consider the trajectory. So that is in fact my Brownian trajectory. So a continuous but not differentiable. Okay, so what is the benefit of this is I can now use the Wiener process, right, this W, to rethink my meaning of this integral. So in other words, I don't want to work with this zeta, right? Because I don't want to work with this infinite amplitude thing. So what I will use the fact now is this W of t I've just shown is equal to the following, right? That's what we just saw. And I'm going to now define this as being equivalent to just this thing, right? By analogy with the usual understanding of an integral. Right, where I have replaced, right, dw, this has been replaced by dw. And what are dw, right? dw is the increment of the Wiener process, right, in time delta t. I mean in time dt rather. dt or ds, right, in time ds. Now, why is this useful? Because if I now think of this integral, right, here I'm saying I have to basically integrate a time series zeta of s. If I want to do this, let's say numerically, I actually want to do it in practice. I can't even realize how to generate this unbounded time series, right, of zeta, which can have infinitely large amplitudes. But dw I can easily construct if I was to numerically try to solve this integral, right, or to construct the integral. Because what would be the integral 0 to t dw? I would discretize the time interval into steps delta t, right? And then this would be represented by delta w. Okay, so for example, if we discretize, I would have, right, this would be like the partial sum. We will look at this more carefully, right? But I discretize the 0 to t as a partial sum of delta w, right? Because delta w is the Wiener increment in time delta t. Okay, and so what is delta w? I know what this is from the previous class, right? Because these increments have a distribution. That distribution is the solution of the Fokker-Planck equation for a small time interval delta t, right? Which we saw is nothing but it's a Gaussian distribution with variance delta t. Okay, so that is if I want to look at delta w square root, which is like the standard deviation, right? This is just root delta t. Okay, so in other words, we've reached here formally, and now I'm saying it's much better to work with this, right? Because I can actually construct this integral. I can give it a meaning the way I would give it for a Riemann integral, right? Whereas here, it's hard to see how to do it because the zeta has infinite variance. Whereas here, I can represent this approximated by the partial sum, where n can be made larger and larger, right? So I break this integral into parts, delta t. In each delta t, this dw is that increment of the Wiener process, right? It's like the Brownian step. It is the Brownian step, rather. And how do I actually do a numerical evaluation? I have to sum up these increments, delta w, and each delta w, I know what it is exactly, right? It is nothing but sampling a Gaussian distribution with variance delta t. Okay, so if I want to actually construct this Brownian path, right, I start with some value for w, start with the initial point, and I add to it a Brownian step. This Brownian step is just is a random number, right, drawn from a Gaussian distribution with variance delta t. Okay, or if you want to do it, let's say in a computer program like in Python, you have a standard Gaussian distribution with variance 1. You multiply it with root delta t, right, that number. And then I just add these up. That's what you're doing here, right? So this is nothing but saying that my Brownian path is a sum of Brownian steps. Each Brownian step is, of course, uncorrelated with the previous one. This I know because the increments of the Wiener process are uncorrelated, right? We saw this in the last class. And so each step is nothing but a Gaussian random number, okay? And if you draw it from a normalized Gaussian distribution, which has variance 1, you have to multiply it with root delta t, okay? So that you get, that is the standard deviation, it gives you the right variance. And this is exactly what you did in your assignment 1, right? Or this is exactly what we saw when we looked at in the first 1 or 2 classes, right? And we tried to understand, okay, if I had to do some kind of Euler integration of the OD dx dt equal to zeta, right? And let's do an Euler integration. Then we saw that if we do the naive thing, the answer would depend on the root mean square displacement of x would depend on delta t. Unless I multiply that zeta, I mean, if I treat zeta as a Gaussian random number, I should have multiplied with root delta t, right? And that time we said we don't understand why this root delta t is coming to give me a converged answer. So now we see formally we're doing things properly, it comes out automatically. Okay, and the way to think about it really is to use the w itself to define the random walk. So in the special case of simple Brownian motion, things are now clear. What we should do is not think of stochastic Brownian trajectories as being a consequence of dx dt equal to zeta, where zeta is delta correlated with the Dirac delta variance, because that is mathematically not digestible. Right? So what we do instead is say, no, the random walk is defined as the integral of the Wiener increments of the Wiener process. Right? And the increments of the Wiener process are well defined. They are just a Gaussian, they are a continuous stochastic process with a Gaussian distribution, right, with variance delta t. So then if I want to numerically simulate a Gaussian noise, a Brownian walk, it's very clear what I should do, right? I should say that the trajectory w is a sum of the Wiener increments, and I can just keep sampling. Wiener increments are nothing but Gaussian random numbers with variance delta t, that's all. And that's exactly what you did in assignment 1. And this is now, so now this is perfectly fine, but only for the simple Brownian motion, right? But what I want to do is consider a general SD with some drift, right, where the stochastic term has some coefficient b which is not 1. So what we'll do for now is extend, right, again proceeding intuitively, that if when I know that a is equal to 0 and b is equal to small a, now I'm talking about, right? In the original SDE I wrote, I had that small a and small b. If small a is 0 and small b is 1, I have normal Brownian motion, and that I know how to deal with. But I will use this idea, let me extend it directly, right, with a leap of faith to consider the general SD, right, and say that I am now going to look at the general trajectory x of t, right, extending to the general x of t process that I started with, right? And I'm going to say that I'm going to study the following process. which I will then try to give some meaning to. Okay. Plus integral 0 to t, again, I'm just rewriting what we had before, but with one important difference now. Right, this is fine. I now have a different way of writing the b part, right, which was problematic. I made one step. I'm going to write this as b of x, comma s, dw of s. Okay, this dw, so I'm integrating with respect to the increments of the Wiener process. This of s is just for you to keep in mind that time is evolving. Okay, as time evolves, you are sampling different Wiener increments. Okay? But this integral, there is no ds coming in this integral. Right? This integral is going to look exactly like we had here. Right? So when if I write this integral, if I do a trapezoidal rule, I will have b in every interval dt multiplied by a particular sampling of this delta w. So what remains to show is, what we have to show still is we can make sense of this integral. We know when b is equal to 1, I've made sense of it already. Right? It's a continuous stochastic process, it is the Wiener process. But when I weight the increments that I'm adding up with some function, right, of time and of the trajectory itself, right? In other words, I'm weighting the noise, then does this still make sense? That's why you will see that we have some complications. But let us write it down for now. And assuming that I can make sense of this stochastic integral, then I can say, okay, what I can really deal with is this stochastic process. And for notation's sake, I will say that this, what I really mean is this, but I can write it in the form of an SDE. Okay? Right, so the mathematical quantity I'm thinking about really is always the integral, because I cannot write some kind of differential equation. But for the sake of notation, for the sake of convenience, not having to write integrals all the time, and also because we find it more pleasing to write it as an SDE because it connects to the usual ODEs, right, in some fashion. So I can write this as in terms of its infinitesimals. Right? So dx is equal to this looks like the usual difference version of an ODE, but now the crucial difference will come here. Okay, and this thing is the correct formal notation for an SDE. Okay, and the crucial difference of this from what we started with is that I don't have that weird quantity zeta, right, which had infinite variance. Rather, I have now the increment dw. Now, of course, what is dw exactly depends on dt. It's again, right, this is just a notation. What it really means is, when you see this, it should translate in your mind as the integral for x. Right? And in this integral, the dw makes sense because if I try to actually evaluate it, I'm really thinking about partial sums, right, over intervals of time, and I can make the delta t arbitrarily small and converge to this integral the way I usually do for a Riemann integral. Okay? And in the integral, I know what these increments are because if I take any given discretization, dw, or I know what delta w is. It's just a sampling of the Gaussian distribution. So there's no infinities anywhere. Okay? Right, so in your mind, what I want you to think of is this dw, remember, has magnitude of what? Right? It's standard deviation, which is root dt. Correct? So this thing, so now you think of it as a infinitesimal equation for small differences. So small update in dx is a velocity times the small dt, that's the usual behavior. But now I have a diffusion coefficient type thing, right? This b, which is like a diffusion coefficient. It's not exactly that, but related to that, right? This thing times the Brownian step. And the amplitude of the Brownian step is not like dt, it's like root dt. Again, as we saw here and as you did in your simulation. So the interesting thing is the strange property of SDEs, which we will see later in the course, comes because dw is like root dt, right? When you think of it in terms of amplitude, not as dt. So it's in fact much larger than this term when dt is small. And if I was to now force myself to write it like an ODE and I divide dx by dt, you will get dx by dt is equal to a plus b by root dt. You see? And as dt goes to 0, that thing will get infinitely large, which is why when you wrote it as zeta, zeta had infinite variance. Okay, so that's why that is a bad idea. And it is when we integrated it out that we got this dw, which is bounded completely, okay, which doesn't have any infinities. But again, right now, all we can say, what we know for sure is that this makes sense if b is equal to 1. Okay, then I can, because this integral is standard, and if b is equal to 1, I know that I'm just adding a Brownian walk to a velocity a. Okay, that I can do. What I have yet to show now is that this still makes sense when each Brownian increment is multiplied with some b of x comma t. In other words, if the diffusion is not constant, but is some function of where I am in space and maybe explicitly on time. Right? So there I don't know whether I can write this yet. We will show that we can, but that's where the complications will arise. Any questions? Okay, so for now, big picture, right? What I want you to think, what we have done here, right? Well, the first important thing that you should learn from this course is writing a stochastic equation like an ODE doesn't make sense. Okay, it's good for motivation. Right? It's how one would. That's how Langevin thought about it, right? That I have an evolution of some particle. It has some deterministic part, which is the drag from the surrounding fluid, right, which I can write with Stokes' laws. That's what he did. But then it has the fluctuating part, which I want to model, right, with some kind of fluctuating force. And that's where we have all kinds of complications. And we see now that if we had to try and push this way of writing, the force would have to have infinite variance, right, but with zero correlation. Right? So there is not, in other words, the time it has to act to make some motion happen is infinitely small. And therefore, for anything to happen, it has to be infinitely large, right? This kind of weird behavior. So dealing with this is strange, right? So instead, the way to think of SDEs is not to think of it in terms of the derivative of x, right? And that's what we have done here using the mathematical theory of stochastic Markov processes, and said that no, I should write it in this way, right, in terms of the infinitesimal increments. So the increment in x has a drift part, which is deterministic, and a stochastic part, and that stochastic part is Brownian increments, right, these random steps, which are well defined because depending on how you choose to discretize dt, this is just a Gaussian distribution, right? So I just draw a Gaussian random number, multiply it with a unit variance Gaussian random number, multiply by root dt and tag it onto the deterministic part. And then I have the freedom, I'm assuming for the moment, that each of these Brownian increments can be weighted according to some function, right? And this will give me a generalized kind of Brownian walk, right, with some drift and with some kind of random motion that depends on space and time. Okay. And I have now got rid of thinking about that zeta, so we will never again have to worry about that. The question now is this a valid thing, right? And what does it mean when I have the b multiplying the dw? Right? When b is 1, we know what to do, but what does it mean when b multiplies it? Okay, so once again, just to recap, we now have a general way of writing an SDE, right, at least formally, where we say the stochastic process x is described in such a way that its increments are given by a drift deterministic part plus the stochastic part, where dw is the increments of the Wiener process. Now we know what to do and we know it makes sense. A can have some value, right, need not be 0, but for the case of Brownian motion, I'm taking A to be 0. Most importantly, B is constant, because with our laws of generality, I take it to be 1. So if B is 1, then x is just Brownian motion. And how would I numerically realize the Brownian motion? Right, so numerically, what I would do is simply add, right, Gaussian random numbers of variance delta t. That's just like saying that, okay, x is equal to the summation of delta wi, I going from 1 to n. Okay, so I'm just stating this explicitly so it's clear. And this is precisely what you did in your assignment 1. Okay? And now you see that if I want to generate it at smaller time steps, like more highly resolved in time, then as I shrink delta t, the magnitude of this dw will go like root dt, right? Because the variance will be like dt. So I have to take more frequent samplings of the Gaussian process. In other words, I'm adding more random numbers, right? Because that's just like saying I take n to be larger, right? I'm making a finer discretization. So as I add more random numbers, that is being compensated for by the magnitude of those numbers going down, right? But as a root of dt. And that will give me the same mean square displacement. So that's what we used to motivate it initially, but now we know this to be true precisely, right? Because W is the Wiener process. So not only will the root mean square displacement converge as n increases, right? But all properties of x will converge. Right? All this in the statistical sense. Okay, so that's what we understand with for Brownian motion. Now a couple of more comments before we go back to the general case. So in your assignment, I'd also asked you to check what happens if you don't use a Gaussian distribution, but a uniform distribution, keeping the variance still as delta t. So in the assignment, the way we phrased it is, we said we took variance 1, but multiply the random number with root delta t, right? It will give you the same thing. So as long as I keep the variance of my distribution the same as this Gaussian thing, I can change the Gaussian distribution to, for example, a uniform distribution. Okay, so so instead of Gaussian, what if, right, we use uniform? So I know theoretically the Gaussian is what it should be. Why? Because the Gaussian is the PDF of the increments coming from the solution of the Fokker-Planck equation. So that's why it should be Gaussian, right? Not because I like Gaussian functions or something. It's coming out automatically, naturally from the Fokker-Planck, right, which we had already solved. Now I'm just asking, okay, if I was to numerically simulate it, instead of generating Gaussian, which is a relatively complicated PDF, can I do a uniform distribution? In fact, the standard random number generator gives you a uniform random number from a uniform distribution, right? And it's actually quite different because the Gaussian, remember, looks like this, right? It has exponentially falling off tails, but it's never zero. So there is always some finite probability to get some arbitrarily large increment, right? Whereas a uniform is bounded like this, right? So if I want this to be unit variance 1, this is something like, I forget, 1 by root 3 or something. But there are some bounds here. You can choose A and B to give you whatever variance you want. But you can see now there is zero probability for having increments beyond some size. Whereas here you always have some probability. There will always be large deviations. So at first glance, it may be surprising that I can replace the Gaussian increments by this uniform increments. Right, but if you've done assignment 1, you would see that this does work out. You get exactly the same statistical behavior, right, for the root mean square displacement. So any idea why this should happen? Those who have done a previous course in probability, right? So you can understand it. So there's of course a formal proof and so on, but one way to understand it is in terms of the central limit theorem behavior, right? So what is central limit theorem? You have some distribution, right, of let's say x, and then I'm looking at y, which is defined as a sum, a large sum of many x's. Right? And x has whatever distribution you like with some finite variance and so on. If I look at the distribution of y, and provided the number of x's I sum is large enough, the y will have a Gaussian distribution. Okay? And we can now relate that to this, because remember the dt is arbitrary, because it's anyway delta correlated. If I can make delta t as small as I want. So let's say I'm going to choose this uniform distribution, okay, instead of Gaussian. You can already see that if I make the time step sufficiently small, it's like adding many, many uniform distributions together. And after some time, it will give you the same answer as taking Gaussian over larger delta t. But again, the delta t is not bounded from below. You can make it as small as you like. So the Brownian walk, right, is a sum of many random steps by definition. So it doesn't really matter what those random steps are. At large enough deltas, you will get the same behavior as if you had used Gaussian steps. And there's nothing stopping me from making the deltas as small as I like. Right? So you can see from this sort of argument that it has to work out to be the same. Now, what converges is only the statistics, because central limit theorem works only on that. Right? The individual trajectories will not be the same. Okay, so if I look at, if I generate trajectories from this, right, using a sequence of random numbers, and I generate trajectories from this, those trajectories will have different properties. Okay, but if I look at any ensemble average property, they will be same, because the averaging is what brings in the central limit theorem. So in the notion of these stochastic processes, there are ideas of weak and strong convergence. So strong convergence implies convergence in the trajectories. That is, the trajectories start being same in the limit. Right? But then you also have the idea of weak, where you are saying only statistics of the trajectories are going to be the same. And for most applications, we are interested in the only in the statistical averages or even the distribution, right? Not in individual trajectories. Why? Because those individual trajectories, of course, depend on the precise properties of these steps that I'm taking, and usually I don't care about that. I only care about the average behavior. But there are, of course, cases where this is not true. So it's important to remember that so if in the take-home message is, if I was going to do a stochastic simulation of some Brownian motion, if I only care about statistical properties, right, long-time behavior, then I can just replace the Gaussian. But if for some reason I'm very worried about individual trajectories, then it will not be the same. So one example where this can be important is in a game. So in physical reality, usually I'm not bothered so much, because I don't care what a particular, let's say, molecule is doing. It has no meaning to me. I only want the average behavior or something. But let's say you are constructing some kind of game where there is a stochastic element. The outcomes of the game depend sensitively on the trajectories, right? And then you have to worry about it. Yeah, so that also explains hopefully what you have already seen, right, numerically in your assignment, that if you replace this with the uniform, there's no problem in terms of the mean square displacement, right? And why that connects to the central limit theorem. Okay, so now let us go back, right, to the general case and try to understand whether we can make sense of this integral and what new problems arise. Okay, so we made some progress in that we have got rid of that zeta, but we now still have to understand this integral. So let's just look at that integral. Okay, now let us try to make, in the usual style of this course, let us try to make some progress and then see if we encounter some difficulties. Okay, so we will define this integral as the limit of the Riemann sum, the usual way one does, right, for a Riemann integral of a partial sum. Right, so our hope is that if we construct a partial sum, we construct a sum over n parts. As I take n to infinity, I get a converged limit, which I can define to be this. Okay, and because of course it's statistical, I will have to say converged in terms of the statistics in some statistical sense. So we'll come back to that. But for now, I can always try to write a partial sum, right? And now again, we had already seen this in the beginning, right? That when I do this normally, I'm breaking it up into parts. There will be a question of where to evaluate b. Okay. Right, so this dw is just the increment of the unit process. Okay, and now this bi has to be evaluated somewhere, right, between si minus 1 and si. Right, so each interval is defined from I minus 1 to I, and then I'm summing it up over n. So this is the usual sum. And as we had seen in the first class, right, if I were to apply this to this integral over dt, then I can evaluate A anywhere I like. The error that arises will behave like delta t square, so that when n goes to infinity, right, remember delta t is capital time integration limit over n. So it will go like 1 by n square, it will disappear. So that's why the usual deterministic integral we can evaluate wherever we like. Okay, you will get the same final answer. Then of course in an actual numerical scheme where I use a finite n, there will be some choice of the best position to evaluate it so that I get the answer for small n. That's a numerical approximation question. But in terms of defining it, this integral is well defined because the b can be anywhere. I mean, the a can be anywhere as long as a is a continuous function. Now here, even if b is continuous, we will see that there is a problem, right? One has to worry about this. So to explore what is the effect of choosing the evaluation point, I will do exactly what I did in the early class, right, for the deterministic case, is to use a Taylor series, because this b is of course some well-defined function of x and s. So I do a Taylor expansion, right? I'm going to call this the partial sum Sn. Okay, so Sn is equal to this. And let me expand the bi. Okay, so I can write bi as b at I minus 1. Okay. Let me put it like this. Parenthesis means I don't know where I'm going to evaluate it. Okay. So this means I'm evaluating it at okay, this is just delta w. Okay, so this is b evaluated at si minus 1. Okay. If you like, let me write it like this. And then I want to find out what happens if I move it by some fraction alpha. Okay, so suppose I evaluated at si minus 1 plus some partial way into the interval, right, by alpha delta s. So now what I would have to do is do a Taylor series, right? I have two parts. I can do the s part and the x part. Right, and then into the delta w, alpha of course. Right, so b at I is its value at the beginning, right, plus its derivative times the increment that I'm making. Okay, and then this delta w is carried over from here. And then I can do the same thing. So this is the part of b that depends explicitly on time. Right, so suppose the coefficient, this is like some kind of, it's giving weight strength to the diffusion. So if this function is like sine t cos x or something, right, so it has a time dependence. That explicit time dependence is here. But it also has a dependence on space, right? So that also I have to consider. I use now small x because remember capital X is the actual trajectory value, but if I write it as a general function, x is just a coordinate, right? So dv by dx, right? And then I should have, so normally I would have dv by dx, dx by ds, alpha delta s, right? So on. but dx by ds doesn't exist, right, in the way I'm looking at it. But I can write the increment itself that corresponds to delta s, right? That is nothing but my delta x, right, which follows from there. So this delta x, the increment in x in delta s is defined by this, right? So I can use this. Okay, and that into alpha delta w. Okay, so alpha delta x is the step corresponding to taking alpha delta s. And then there will be higher order terms, okay? But I'm not, as we will see later, when I take n going to infinity, I'm going to write the delta s as capital T over 1 by n. So all the deltas will get 1 by n. So if I have higher order terms, I'll get things like delta s square, all those will drop out in the limit of n going to infinity. So you don't have to worry about them. So it's just these three terms that I have now instead of only one term, okay, by doing my Taylor series expansion. And now what I'll do is replace the delta x, because I know what to do with delta s, I know delta w, but delta x I replace from here. So if I replace this, right, okay, this in turn is right. So delta x will have an a delta s, and a b okay, you will have this gets replaced by these two terms. Okay, so finally I have three terms, right? I have term 1, I have term 2, and I have term 3. Is that okay? And now what we want to do is, let's see what happens to the mean of this partial sum, okay, because the integral only will make sense in some ensemble averaged way, right? So again, I'm not defining the integral, we are just exploring, right, what the integral means. So if, assuming I can write this, what is the average Sn, right? The average partial sum. So I can apply the mean, right? So let's take this first guy. Right, so these two terms are similar, right? Okay, so I have one term which just has delta w. I have one term which has delta w, delta s, dv by ds, and dv by dx in the a part of it, the deterministic part. Right, and then I have another term okay. I hope I've not missed any alphas or something. Okay, so now you see the interesting part. So now I can try to evaluate these ensemble average. So what's the first guy? Right. So when you see such products, the first thing to ask yourself is, are these correlated or not? Okay. So are these two things correlated? Right. Think about what the increment is. Right. So by definition, the increment dw is uncorrelated with itself, with anything in the past. And this is evaluated at the past, because I'm evaluating b is of course some function of the Wiener process itself, right? So b is a function of x, and x, the value depends on the Wiener process. So b depends on w, that is true, right? But the question is now, where is b being evaluated, right? It's evaluated at the current time si minus 1. That's the time at which I toss the random number. So the Wiener increments are, each of them are independent. That property means it's also independent of this, right? Because it's independent of all the past steps, and this is also part of the past. Right? So if you imagine this is si minus 1 and I is over there, right? I'm evaluating b here. And at I minus 1, at this time I toss delta w. So the value of delta w has nothing to do with b at this time. But however, b at a future time is correlated to delta w, because the delta w I toss is being fed into x to give me the value of b at the new x. Right? So the future values of b will depend on what I toss here. Right? Because what I'm tossing, the Brownian increment, I realize at I minus 1 is contributing to x at I. Right? And therefore to b at evaluated at I, or anywhere in the interval. But at the beginning of the interval, everything is uncorrelated to the increment I generate, right, at that time. So these things are uncorrelated and they go to 0, right, because they are uncorrelated. Now you look here, right, these again I evaluate at the beginning. In any way, so they are uncorrelated. I'll then get dw, ds, ds is deterministic. Once again, it will go to 0. I mean, of course, uncorrelated, and the fact that by definition this is 0. Okay, so uncorrelated, and then it just breaks up into mean of this and mean of that, and the mean of the Wiener increment, of course, is 0. Same thing happens here, but here it's not the same thing. Okay, again, this is at I minus 1. They're uncorrelated, right? So this thing survives, right, because it will become alpha whatever the average is of that. Okay? Because remember, when I say average, it's like I'm generating many trajectories of that, right? So at I minus 1, different realizations will have different values for this quantity, but I take its average, it's some average. Okay, but then I'll have average of delta w squared. And what is that? What is that? It's a variance, right? Which is delta t or delta s. Okay, so the important thing is, if I consider this integral and I try to define it as a Riemann sum, I will see that the answer, the mean, right, will depend on where I evaluate the b. If I choose a fraction alpha to evaluate it, right, I get no corrections from here, but I do get some lasting correction. And that correction goes like delta s. Right, so that means when I write delta s is equal to t by n. Remember, t is the integration limit, right? 0 to t. So t is the full time interval, and t by n is nothing but delta s. So when I do the partial sum, okay, and I take the limit n going to infinity, this will survive, right? Because this will be t by n. So I am summing up. This is some finite value, right? And I'm summing n things over t by n. So I will survive. Okay. So you will get an error, if you like, right, that goes like alpha times the mean of this. Okay. And then that t will survive. So yes, I mean, you can certainly say it's less than the max of this value. Okay, so there will be some error which depends on this. So the alpha plays a role, right? This is what we had seen along similar lines at an earlier class, right? But that basically the choice of evaluating b will matter, and I'll get different answers. In other words, if I try to write an SDE in this way, it's not enough for me to just write this, because remember, this has no meaning. What has meaning is the integral, and I can define the integral. I'll get some definite answer provided I say where I should evaluate b. Okay. So whenever you write the SDE, it has to be accompanied by a statement of where is this evaluated. Is this evaluated at the beginning at which I toss the increment or somewhere midway in the interval. Because that will have consequences. And of course, the consequence depends on the derivative of b. Right? That's what we have seen from this simple demonstration. Okay? And therefore, if it's a Brownian motion, it doesn't matter. You see, immediately that becomes clear. So if b is constant, let's take equal to 1, right, for Brownian motion. Then that dB by dx disappears. Okay? So then there's no problem. That's why people can do Brownian motion. We don't have to worry about it. There's nothing to evaluate, right? It's just 1. So the problem arises only if this effect, that thing that gives you the diffusion, right, the diffusion weight, I'm not calling it coefficient because it's not exactly that. It's closely related, as we will see. Okay, but if this b, right, the second moment of the steps, if that depends on x, not even explicitly on time, right? You see that also dropped off. So the dependence of b on time explicitly doesn't contribute anything. So if you have a diffusion behavior that is a, let's say, a sinusoidal function of time, no problem. It's only if it depends on the x itself, right, that you have this issue. That then one has to be, I mean, the definition of the kind of trajectory you get and what process it is depends on where you choose to evaluate b. Okay. And those of you who have encountered this before, that this kind of system where b depends on x, right, which is the process, is called multiplicative noise. Okay, so if the b is not a function of x, it could be a function of time. If it's not a function of x, then it's just additive noise. Because you have some stochastic process x to which I have a deterministic part. I'm just adding some Brownian forcing to it, and the Brownian forcing, that effect of the Brownian forcing doesn't care about x. It's just adding to it. That's why it's called additive. But when you take the Brownian increments and weight them with b that depends on x, what you're saying is the effect of the noise on the process depends on the process, depends on the value of x. So for example, if x is large, the noise it experiences is large. If x is small, the noise it experiences is small. Suppose you have such a process, right? If you think about, I mean, let's say the wealth, right, in someone's wealth or something. The less money he has, the fluctuations in it, his amount is small. He has a lot of money, he also has large fluctuations. Okay, so if you want to model such a process, it would be something multiplicative, right, where the effect of the fluctuations is weighted by the value of the process itself. Okay. So such multiplicative processes give you more complex behavior, right? They are in a way nonlinear, right, because the outcome of the noise depends on the process itself, right? There's something nonlinear about that. And that is where we have this problem, right? Because it depends on where we now evaluate that coefficient b, at what value of x. The value of x at the beginning of the discretized interval or somewhere in between. Or okay, so this is the quite fascinating mathematical discipline because this is where you kind of explicitly make a choice. Right? It's not something that is defined. Right? We have to choose. So there are a couple of, so you can of course make any choice, right, at this point and then proceed. But there are two important choices that are used, especially in applications. So the simple case is alpha equal to 0. That means I evaluate b at the beginning of the interval. If I do that, looking back at what we just did, you will see that the average of the integral is 0. Right? So the average of Sn is independent of n is just 0 because if alpha is 0, the only term that survives is b at I minus 1 times dw. dw is always independent of anything at the beginning of the interval. So automatically, if you define your integral with alpha equal to 0, then the mean is always 0. That fluctuating part doesn't do anything to the mean. It only gives you variance. Okay? But that's like saying my noise is always additive. Okay? Because if I'm adding noise and the noise has 0 mean, then the mean of whatever process I'm adding noise to will also stay 0, or it will stay a dt. That's the other way. If I add a deterministic part, the mean of the process will be whatever solution I get from solving the deterministic ODE. The noise I'm adding to it just gives me variance. Right? This is the kind of very simple stochastic modeling. Right? So for example, if you think of, I have some population of rabbits and they are increasing in time. If I want to do an ecological model, I can write deterministic equations. I'll get exponential growth for example, or if I do Lotka-Volterra, I'll get predator-prey interactions. These are deterministic equations. Now you say, okay, I just want to look at what could be the variance about this population, accounting for some fluctuations. You can put additive noise to Lotka-Volterra. You will get similar limit cycle behavior, but with some variance. Right? And this is useful if you want to quantify variance, how it depends on the deterministic part. But now if you say that variance also depends on the numbers, right, then you get completely different kinds of behaviors. Okay. But if you take alpha equal to 0, that doesn't allow there to be this kind of behavior, right? The mean always becomes 0. And this thing is called the Ito integral. Okay, so that integral b dw, right, b of x comma s dw, if I take alpha to be 0, if I define it that way, I get what's called the Ito integral. That's how Ito defined it. And the nice thing is the mean is 0. So that allows me to prove things mathematically easily, because whenever I take the mean drops out. And the other choice, alpha is equal to half, is the Stratonovich integral, right? And this half we will motivate in the next class why this is a special choice. It will turn out that in physical problems where we want SDEs to satisfy the mathematics of ODEs, one has to think of alpha equal to half, right? Because it gives us the same rules of calculus. We'll see why later. But when we actually want to do numerical computation or prove things mathematically, the Ito integral is much easier to work with. Obviously, numerical computation is obvious, right? How will I evaluate B at the midpoint when I have not yet advanced the process to the midpoint, right? I know B at the current step. So how will I find out? So then I'll have to do some iterative thing, right, to guess what the value is at the midpoint and then take it and so on. Right? Whereas if it's alpha 0, there's no problem. It's like an Euler integration. This is like some midpoint rule where I have to do some tricks. Okay, so let's stop here. We made some progress in this class. In the next lecture, we will look at the Ito integral, define it precisely, and then see why the alpha equal to half case may be useful. Thank you.